All right, let's get to some more fundamental relationships. Now, we've already discussed this, that the frequency can be expressed as 1 over the period, and that the angular frequency is just 2 pi times the frequency. In other words, if something goes around 5 times per second, or it goes through a cycle 5 times every second, what would its angular frequency be? Think about that for a second. If its frequency is 5 cycles per second, its angular frequency would be 10 pi radians per second. Those are really saying the same things, but using this omega angular frequency actually allows us to do a lot more stuff with mathematics. So this is a lifesaver when it comes to making the math easy. Okay, now what we're going to do next is expressing the displacement, the speed, and the acceleration as functions of time. You will find that right here on the notes, part B. So if you're following along, you can keep the notes right there. So we're going to express x, v, and a as functions of time. So one thing I wanted you to notice about this simple harmonic oscillator are a couple things. I'm going to displace this downward like this. Notice that if you just graph the displacement versus time, it traces out a sinusoidal function. Sine or cosine, either one will work for this. So we can see that the displacement is actually a sinusoid. And that is very, very useful. We want to be able to express what the heck's the amplitude. What is the amplitude for the horizontal motion? Now, in other words, what's the farthest, when we're back to our circular motion here, let's go back to take a look at that. So this line right here represents the 0 in the x direction. What's the farthest that this thing gets away from that 0 in the x direction? Well, you might say that, well, according to this, is just the radius of the circles as far as it gets away from this x equals 0 line right there. So, in fact, we can take that right here. So the radius of our circle, if it's going in a circle, will be equal to the maximum displacement, the amplitude. So here's how we can express this. And now this is going to seem like a big jump to many people, but I will explain in more and more detail how this equation comes about and all the other equations. So this is basically our fundamental equation relating position and time. It's right here. If you zoom in on this, you can see basically where this expression comes from. A is the radius. It's the maximum displacement that this object gets out to the right there. Omega t is the angle. And of course, omega t is changing. The angle is changing in time. And x is just a cosine omega t. So I'm going to explain momentarily where this term phi or phi comes from. So we got A is the amplitude, the greatest displacement from equilibrium from the 0 point in the x direction. Omega is the angular frequency. It's how many radians per second the object moves through, and where 2 pi radians is a complete cycle. And we also have this thing phi, or some people pronounce it phi, which is called the phase angle. And this I'm introducing because it comes through in a lot of other wave theory and physics, but it's simply how far through the cycle, the number of radians through the cycle at t equals 0. So in other words, if phi was 0, it starts at the beginning of the cycle at x equals a. I'll explain that in a minute. It's just at the beginning of the cycle if that's 0. If this phi is pi, that means it's halfway through the cycle at t equals 0. If this is pi over 2, how far through the cycle would we be at time equals 0? Think about that. If this were pi over 2, if phi was pi over 2, how far through the cycle are we at time equals 0? Well, a full cycle is 2 pi, so pi over 2 is a quarter of the way through the cycle at time equals 0. For most of our applications and most of our problems, phi is simply going to be 0, so it'll just be cosine of omega t, but I wanted to introduce this here so it won't be so foreign to you. You can also use x equals a times sine omega t, but I'll tell you why we're going to default to this one right here. Our default's going to be x equals cosine omega t, and notice I'm already starting to leave out the phi because we'll see it very rarely. And this is because this is much easier to produce in the lab. So here is why. I'm going to pull this down to the maximum displacement so that at time equals 0, what is my displacement? It's the amplitude. So let that go. At time equals 0, x or y, whatever you choose here, is the amplitude. So notice that if we use this at time equals 0, what is omega t at time equals 0? It's 0. What is cosine of omega t? What's cosine of 0? Cosine of 0 is 1. So that is a situation where x equals just the amplitude. We can produce that in lab just by pulling our object to the maximum displacement, pulling it down here, and releasing it at time equals 0. When I let it go, boom, that's called time equals 0. Now, you can make this happen so that it does x equals sine omega t. You can use this, but that means you've got to start it at position equals 0, because let's say if we use sine omega t, at time equals 0, the position will be 0. So we have to give it some speed at time equals 0. We would have to start it off right there and give it some initial speed. So we'd have to shoot it at some exact speed that is known to control the simple harmonic motion. That's really hard to get an exact speed, to shoot it with an exact speed at when it's at equilibrium point. It's much, much easier to pull it down to just a known distance, which will be our amplitude, our maximum displacement, and just let it go from there. So that's why we prefer to use cosine omega t, because it's easier to produce in the lab. That's why we do that. So notice that if we use the cosine function, our maximum value is a, it's easy to see, and at v will be equal to 0 at time equals 0. So that's easy to produce in the lab. Now, once we do this and we define, this actually is our equation right here for the position of an object in simple harmonic motion, we get to either derive or memorize these equations. We want to create these equations such that x is equal to 0 at time equals 0. Beginning with, we've already established that the position function is a times cosine omega t. If it starts at the maximum displacement, a, it'll be back at a when omega t equals 0, when omega t equals 2 pi, when omega t equals 4 pi, 6 pi, 8 pi, etc. It'll be back at this maximum displacement simply because cosine of 0, 2 pi, 4 pi, 6 pi, 8 pi, those are all equal to 1. Now, how do we express the speed or velocity? You just take the first derivative of this to get this. Notice first derivative of cosine is sine negative. It's a negative sign, so that's where that negative comes from and the sign comes from. And then you have to use a correction factor. Well, the a is still in there, but a correction factor of omega using the chain rule to give you that omega here. So the velocity function is as simple as negative omega a sine omega t. If you don't know how to derive this, unfortunately, you have to memorize it. Now, you could actually just use this whole setup right here and rederive it. You can prove that the velocity is negative omega times a times sine of omega t using this, but it's way easier with calculus. So you can derive that. Now, how do you get the acceleration? The acceleration is just the second derivative of this, which is this. Notice you take the negative, that omega stays there, but then you have to take the derivative of sine, which is cosine, and then multiply by correction factor again, which gives that negative omega squared. So this is the acceleration function. Let's just make sure this is right. To be simple harmonic motion, notice that we have to have a function where a equals some negative constant, which we always use omega squared for, times x. Is this true for that? Well, this right there is x. Notice that our a is, here's x again, it's just this negative constant right there times x. So yes, in fact, this is these are the equations of kinematics for simple harmonic motion. Now I'll ask you this to see if you get this. Can you use delta x equals v initial t plus 1/2 at squared for simple harmonic motion? Well, you can only use that if the acceleration is constant. And notice that, according to this, the acceleration is a time-dependent function. The acceleration changes. So answer is no, you cannot. Acceleration is not constant, so you can't use kinematics based on constant acceleration, which this is an example of. You can use the other kinematics, which we've just outlined right there, the kinematics of simple harmonic motion. All these equations work. This is kinematics of SHM. You can use all these equations, but you can't use the equations we used before. You can't use the grand mammy equation, v final squared equals v initial squared plus 2a delta x. You can't use granddaddy, this one right here. Can't use either of those. So you can only use these. So these actually summarize all the kinematics of simple harmonic motion.